So thank you very much for the lovely introduction, no pressure. It's wonderful to be here and an honor to be asked. I actually have the clipboard from the first machine learning summer school I went to when I met Emily, so it was from 2009, so like literally 10 years ago. And much of these slides are the same. So this talk is fundamental, important stuff. Some of you will know a lot of it already, but I'm not making apologies for covering this talk because it's stuff I use every week, and I'll try and point out that there are things in this talk that I keep thinking about. And also, a lot of us as experts are going to be the future teachers. The needs of data science are growing so quickly that even with all of us here, we're not enough. We need to have a multiplying effect and teach people how to do things. And part of that is teaching them how to think about things and check things. And these basic things that I'll talk about in today's talk are really useful for checking things and understanding what's going on. So really useful stuff. My future talks will be more about the sort of frontier of machine learning and current research. So as John alluded to, this term Monte Carlo, and a lot of these methods sort of go way back. They go way back before the 20th century, but the Monte Carlo term came out from the sort of Manhattan Project in the 40s and 50s. And there are many anecdotes of sort of people using Monte Carlo methods to get insight into what was important then. So Enrico Fermi, one of the people working there, wanted to understand neutron scattering, amongst many other things, and he would come in and tell his colleagues, oh, I predict this is what will happen in an experiment, and he was often right, and they thought he was this amazing mathematical genius. He must have done some amazing theory to figure out what was going to happen. But in fact, he was simulating, using his hand adding machine, what would happen in the experiment, and then just seeing what would happen. And that's because he had insomnia, and he could stay up late at night using a hand adding machine. But now we have ridiculously powerful computers just everywhere, where it's very easy to simulate things and see what happens and get an understanding for systems. So that's the first lesson we want to learn, and we want to think, well, how is this relevant to machine learning? So in this talk, the first bit, I'm just going to give a couple of examples of looking at samples and seeing how that's a useful thing to do. We'll then talk about computations we might actually do, and some of the basic methods that I'm aware a lot of people in the room know, but hopefully you'll learn something about the way I think about them, different way of looking at them, and there'll be some examples. So with ridiculously small code that I'm not expecting you to read, here's the first example. So you can imagine you're teaching an intro machine learning class, and here is a complete implementation of a deep neural network. So these two lines of code say, get the previous layer, a linear combination, apply an activation in a for loop, do that as many times as you like. So there's a deep neural network. You can put autograd around that, and then you can fit it. And so it's true that the machine learning code is often very small. If I look at it, sort of large industrial systems, you have a machine translation system that sort of seems complicated, but the Python code defining the model that gets compiled to fast code might only be a few hundred lines, and there'll probably be thousands of lines of infrastructure for like getting the data in the right place and processing things and stuff. So our code is small, and yet it's quite hard to know whether we're doing the right thing, and it's a big problem in machine learning, working out how to debug things. So, our students written this neural net code, they've defined a couple of activations, ReLUs, linear units, and like, is this a sensible model? And you could fit it and see what happens, but fitting neural networks takes a long time, and it's not a particularly good strategy to just fit things, see whether it works, go back and change some random stuff, and fit it again. Well, we do that, but it's not a good strategy. And one of the things we can do is just say, well, this is a representation of a function. Is it a sensible space of functions? So there are going to be some weights in this neural net. Here is more code than the neural net code to just set up an example. So I'm drawing 6 different functions in this loop. I create some weights, and I'm constructing a ridiculously complicated neural network. So there are 4 sets of weights, there are 3 hidden layers, and I'm applying ReLUs at each layer. So I'm trying to build a really complicated function, and I'm going to just plot it on the x-axis between -2 and 2. So in this plot in the top right, I've got 6 random functions drawn from this deep neural network with 4 layers and ReLUs and stuff. And yeah, I've done something really wrong and stupid because all of these functions go through the origin, and they're just piecewise linear. They've got a different slope for the negative values and the positive values, and that's it. So I've done all this neural net stuff, and my functions are all really boring. So I've done something wrong. Now, if you're on top of all the neural net stuff, you might go, oh, I immediately know what you've done wrong. You don't need to look at samples. I could have done that, told you that. But we all make silly mistakes all the time. And when you look at this code in small print, it's like, well, where is the mistake? Where do we look? So it's good to just be able to think, what are the bits we can pull out and look at? So in this case, the problem is that my neural net's too simple. I've got weights hitting these layers, but I don't have bias units. And often people miss out bias units in the maths and papers because it's sort of clutter. But it turns out they matter here. So change the code slightly so my neural net takes biases, and I take a linear combination plus bias units and take the activation. But apart from that, the code's all the same, and suddenly I get a rich variety of functions, and it makes sense. And I go, okay, this is an architecture where if I throw random weights at it, I get sensible functions. This might be an architecture where I can learn functions. I'm not putting all of the sort of parameter space associated with trivial functions that are obviously wrong. And in the 90s, if you look at the neural net literature, people like Radford Neal and David Mackay, their papers were full of understanding what the space of functions were like and building that up. And there's much less of that in the literature now, and I think that's a shame. There are recent examples, so like Rich Turner in Cambridge has very nice work on conditional density estimation, where he looks at the samples and then uses that to guide the parameterization when he's building a neural net. So that's my first example. There's a lot of stuff on Bayesian statistics in the summer school, so I'll give you a Bayesian example as well of sampling. So here is a linear regression model in 1D. So we've got a slope and an intercept, y equals slope times x plus intercept. And if we were Bayesian, we would put a prior on what possible functions we thought. So the simplest thing we would do is just go, oh, I'll just put a Gaussian distribution on that number and that number. So I've got a two-dimensional Gaussian distribution on a vector of two parameters, and I could make one up, write down that prior, and then I could draw samples from those vectors, and I could say, what does this prior look like? So here are a whole bunch of random lines in gray, where I get a slope and an intercept by sampling from this distribution. I plot that line. I draw another vector of length 2, which gives me two parameters. I plot that line, and so on. And I immediately see stuff about my assumptions. So all these lines are bunched up here around the origin, and I am ruling out functions that sort of go, the y equals 4 function is sort of not very plausible. And I could think to myself, is this a sensible prior? Does that actually reflect my beliefs? Is this location special? And maybe not for many problems. And we would want to go beyond this in many ways, but for the moment, I'm going to stick with this stupid prior, even though for most modeling problems, we would want to add a load of stuff to our model. So looking at the prior is a sensible thing to sample from. And then you've had some very complicated talks on how to do inference and compute posterior distributions in models. So for linear regression, here's what we'd do. We'd get some data, these black points. So those are observations, yn, which evaluate the slope and then add some noise. So here I've simulated an example data set. I can test my code on some synthetic data. I've got the lines that I thought were plausible before. And what I've drawn in purple are samples from the posterior distribution. So I've got a distribution here over the two numbers, the slope and the intercept, given the black data points. And I'm drawing samples from that distribution. And you can't see what's going on because it's tiny. So I'm going to zoom in to that region and have a look. So here's exactly the same plot as here, but zoomed in. And here in purple, I have 12 samples from this posterior distribution. So it's a two-dimensional distribution. I get a slope and an intercept, and I go, OK, that line could go through these data points. This other line could go through those data points. I don't know where the underlying line is. So I actually generated these points from the blue line, but you will never know what that line is. All you can do is say, here are some plausible possibilities. None of them will be exactly right, but they're plausible. And that's something as a physics undergrad I used to literally do with a ruler. So I would draw in my lab book my data set, and I would put down the ruler and say, well, what are the possible fits, and what would the physical consequences of those different fits be? But now with bigger models, we can get computers to draw these samples for us, and we can imagine different possible worlds we might be in. So we want to know how to do that for interesting models, not just linear regression models with slightly dodgy assumptions. OK, so I've got a quiz for you, so I hope you've been paying attention. Here I've got a linear regression set up where I'm drawing from the posterior given this data set with these strong assumptions. And often what happens is we make strong assumptions that turn out not to be true. So imagine that we've got this data set which is clearly nonlinear. I've got all these observations with quite small error bars, so I can see there's an underlying curve there. But pretend that we just ran the same linear regression code against this model anyway. So I'm going to assume there's a straight line underlying this data set with the prior I showed you. I'm going to compute the posterior distribution, and then I'm going to look at what are the possible fits through this data. And think to yourself, do you know what would happen? What would those samples look like? What would the possibilities be like? So I've got some options for you. Maybe option A, we would match the top bit of the data set. Maybe option B, we'd match the middle of the data set. Option C, the right-hand side. Maybe all of those things could happen. When we draw different samples, we would see lines like each of those. Option E, I'm fooling you there's something else that would happen, and if you were to draw a purple line, it would look different to some of those somehow. Or option Z, it's a bit early in the morning still, you haven't had enough coffee, you're not sure yet, but you have to vote for one of these options. So I'll start with option Z. Who doesn't know who would need more time? Not quite sure. 3 of you. The rest of you are all perfectly certain. Brilliant. Okay. Who thinks it's option E? None of the above? 2 of you. What would it look like? Okay, you just think it would be something else, but you don't know what yet. Who thinks all of these things might happen? Okay. 22 of you. Okay. Who thinks that you might see things like option C? Option B? 36 of you, great. Option A? 2 of you, okay. And a lot of you are big liars because you didn't put your hands up. So yeah, I think it's natural not to be sure about these things. Sometimes, I think I want to try this to be sure, to know what will happen. So, I wrote the code and I wrote the sampler, and this is what happens. So here are 12 independent samples from the posterior distribution. And they are all so close to each other that from where you're sitting, it probably looks like one purple line. So Bayesian machinery is not magical pixie dust that solves your statistical problems, where if you're doing the wrong thing, it will suddenly fix things up for you. So if you have a model that assumes there is one line, it isn't going to create for you some ensemble that will match different bits of the data set. It is going to say, okay, none of these models are that great. Here I've got this enormous outlier where this model is deeply unhappy, but it has to do something. And if it went for any of the other options, those outliers would be even worse, and the likelihood of that explanation would be tiny. So what happens when you draw samples is you're rammed into the corner of the least bad explanations. There's a very common problem in that when we're doing machine learning, our models are almost always somewhat simplified from the truth. If we have a probabilistic model of language and we're doing machine translation, our model is probably not a super accurate model of exactly how German works. We've probably made some simplifications, and our model isn't going to know everything about German or English. And so we need to worry a bit about blindly using statistical techniques that assume things are correct. And when you start with the simple examples where you can see what's going on, you get an intuition for that. And a whole chunk of you already know. Okay, so the first part of the talk was just saying, please visualize things, find any way you can to look at things and draw the samples. But a lot of what we do in machine learning is computation, coming up with numbers. So I'm going to move on to looking at the sorts of computations that we might make before talking about the methods. So when people say Monte Carlo, what a lot of people mean is basically the equation on this slide. People use it more broadly as well, but sometimes when people say Monte Carlo, they mean specifically this. So it's about computing averages, and averages can be expressed as integrals or as sums. Here's the integral version. I've got an average under some distribution pi of some function f. So for example, I might want to know what's the average height of people at Machine Learning Summer School Africa. So that's actually a sum rather than an integral, because I can go to each one of you in turn and measure your height and add it up, and then I would take the average. You could imagine once you've got a really enormous population, it looks like a continuum that I'm drawing things from, and I'm going to get an integral. And large sums and integrals, as we heard in the previous tutorial, are difficult to compute. They're intractable. I can't possibly, in the time in the coffee break, get round all of you and hold up a ruler next to you and measure your heights. But I can obviously get a pretty good idea of a large sum or average by surveying or polling or sampling. So I could just grab 12 of you at random and measure your height accurately. So I could take a sample of S of you, like 12 of you, sum over just the heights of those particular individuals, measure a function of those individuals, and take an average. So if I do that, I've done a Monte Carlo estimate of the heights of people in this room. And I might have to be a bit careful about how I do this sampling step. So in general, I sample the input to my function from the distribution. Here, I'm going to sample a person and measure their height. If I just go to the front row and pick the first 12 people, I'll get the height of keen people, or perhaps the height of short-sighted people, I'm not sure. But there'll be some confound there that means that I might bias my answer. And so I'll want to try and get a fair sampling from the room. And of course, some people haven't showed up to the talk, and maybe people who are lazy or not engaged with the summer school have different heights as well. So in general, making surveys is difficult, and that's going to come into our computations as well. We have to think about how we draw the samples. But if we think we can draw the samples, this simple idea of just taking a survey gives us unbiased, formally unbiased estimates of integrals, and the bigger we make this number, the smaller our variance goes, so without writing new code, we can get better estimates by just running for longer. So here is an example of this idea in action. Let's have this linear regression example again. So I've got a data set, and I want to do something with it. I'm going to make a prediction. A lot of machine learning is about predicting what happens in future. So I could boldly, probably it is bold if I'm going to make linear assumptions, but I could boldly extrapolate to this test location x star and ask, where is the underlying function at this location? Or if I were to run an experiment there and get a new observation, where would it be? So formally, if I want to predict a new output at that test location, given what I know, that probability is given by this integral. So probability theory tells us that we want to compute this integral, and we want this average. And it's the average of the prediction we would make if we knew the parameters of the line, if we knew the slope and intercept. But we don't know the parameters, so we average different predictions under different parameters weighted by how plausible they are. And that's an average, and we can replace this formal average with an empirical average, an average over samples, where we just draw plausible parameters given the data. So here are 12 plausible parameters from the data. I slapped my ruler down 12 times and drew 12 different lines that all sort of go near my data and are all plausible. Each of those in gray makes a different prediction. So if I assumed the top line was correct, I'd get this gray bell curve that says, well, these measurements are noisy, so that's what would happen if that's where the line was. But if that bottom line was true, I've got a different bell curve around that bottom line. So if I knew what the line was, I'd know how to make predictions. But I don't know what the line is, so I'm going to have to smush all of those predictions together and compute that sum, which would give me this green curve. So my true predictive distribution is going to be broader than the noise level of the problem. It's going to take into account that when I'm extrapolating, I don't know where this line is going to go. And the probability theory takes that into account for us. And if I can draw the plausible samples, I can then just do this simple averaging without sort of deriving anything complicated. So here is the predictions I'd make if I drew 12 samples. And the joy of this is that I can just run my code for longer. So here is the same figure, but with 100 samples, and I get a much nicer looking curve. If we do linear regression with Gaussian noise, this predictive distribution is a Gaussian. In black, I've shown what the true answer should be, so we've got very close. Now, Monte Carlo is not way to compute things to 6 significant figures. If I wanted to make my Monte Carlo estimate, the green curve, equal to the true curve, the black line, so you couldn't see the difference on the slide, I might need 100,000 samples. I'd need to sample for a really long time. But as far as telling someone for sort of policy purposes what you think is going to happen, it's going to be roughly around here, but this is how uncertain I am. The 12 samples was plenty good enough. And this is used in stock forecasting if you want to plan what your warehouse inventory should be. A standard thing to sort of do in operations research is to roll a model forwards, sample different possible futures of what your stock levels might be, and for each one, look at the consequences and think, how bad would that be if that happened, and decide how conservative you want to be. And you probably don't need to roll out many different possible futures before you've sort of got an idea of what sort of things you need to worry about. Okay, so for this model, why do the Monte Carlo at all? I've got this black line, I've got the right answer, so I should just use it. If you can compute everything, then fine, you don't need Monte Carlo. But basically, linear regression and the Gaussian processes you heard about last week, and maybe 1 or 2 other models, are the only ones that you can compute everything exactly for. And as soon as you make a model at all complicated, which means at all realistic, you've put in any of the details that a responsible statistical analysis would actually contain, you can't compute exactly how statistics says you should make predictions. So I've got some examples here of some things that could go wrong. We're assuming we've got noisy outputs drawn from some distribution. So this function is our underlying model. It could be a straight line or a linear combination of our inputs, and we'll have a noise model. If that function isn't linear in the parameters of your model, then you probably can't analytically work things out. So as soon as you put a neural network in there or anything like that, you're in intractable land. If that noise isn't Gaussian, then again, usually we can't push everything through the maths. Maybe we think that that noise level is Gaussian, but we don't know what it is. So as soon as we need to put a prior over what different noise levels we think there are and do inference on that as well, unless we very carefully set it up, we might introduce intractability. These parameters in the model, there might be large sets of them, and we might think we need to put a hierarchical prior on those, put structure into our model. So we say, oh, here are the weights we think are plausible, controlled by some more parameters or hyperparameters. And as soon as we have that sort of structure in our model, again, doing joint inference over everything we don't know can get hard. And then there are all sorts of other things that will realistically go into a data set. So the observations might get corrupted. Maybe some of them aren't noisy observations of your line, but they're just big outliers. Things went wrong. So there's an underlying binary variable you don't know that says, is the observation a good observation, or did it get corrupted with some much larger noise variance, sigma n? Or your inputs might be corrupted, and so on and so on. I'm sure that some of you will have done this sort of analysis and will know the extra things that you've put into your models. So there are all these choices in a model, and in other talks or in the textbooks, you see the different ways of formalizing these. So people write down all of these choices, and then they describe those using different technologies. They might use graphical models to say, here are all the underlying things that are behind my data and how they're related. They might use computer code. So they might use a probabilistic program where they say, here is a program that generates example data, but with a load of unknown settings within that program. And again, if you've done that, you better run the program a few times and look at the sort of output it generates before you start doing computations. So whatever your formalism, you build up some spray of maths that says, here is the joint probability of everything that is underlying my data and of my data. So you say, here are the sort of hyperstructures I think are plausible, the weights I think are plausible, the noise levels, the outlying noise levels, the underlying corruption probabilities. Finally, if I specify everything, how do I think my outputs were generated given I know everything else? If I know all my parameters, my input locations, which examples were corrupted, all the noise levels, then I can write down a probability of my data. So that's the main task that you as a statistician have to do. You have to say, if I knew everything, if I knew all the underlying choices behind my data, what's the joint probability of all that stuff? And so for this talk, I'm going to assume you've done that and not cover the slides with this sort of notation, but collapse it all into something simpler. So we're going to assume we've got some data that we've observed, some inputs, some outputs. There's a whole spray of things we don't know underlying our data, parameters, noise levels, which examples were corrupted, that sort of thing. And I'm going to call all of those things theta. So theta is everything we don't know. And what we're interested in is being able to look at example explanations of our data. We've got a distribution saying, here are the plausible settings of everything you don't know, given the underlying data set, and Bayes' rule gives us that probability. And with apologies to John, I am not going to talk about computing this lower quantity, the evidence of the model, which is important, and I will refer you to John's talks for that. For this talk, we're going to look at the top line, this joint probability of everything that we write down, so this spray of maths along the bottom. And that's a function that we know how to evaluate. So for a given data set and a given parameter, we can evaluate this joint probability, or I've written it like that, which gives us a compatibility between all these underlying choices and the data set. So often, we have some distribution that we're interested in, where we can evaluate it up to a constant, and the algorithms that we talk about often don't need to evaluate this constant on the bottom. And so this unnormalized function pi star is often the thing that we pass into our algorithm. We give it a function handle to this function, which in the context of Bayesian inference is this joint probability over data and all the things you don't know. But Monte Carlo methods aren't just used for Bayesian inference, and they're often used in other settings. So that's why I'm writing it in this more general form. And for the Bayesian inference problem, this normalizing constant is super interesting, but we're not always doing Bayesian inference, and so it's useful to know about the other algorithms as well. Okay, so it's an idea of the computations. We want to be able to look at plausible underlying futures. We want to be able to average over those and make predictions. How do we actually go about doing sampling to do these things? How do we generate the samples to simulate data and just look at it and go, is this underlying system plausible? And then how do we sample from these much more complicated distributions? So what I want to do is make sure everyone's aware of the basics, algorithms, and the pitfalls and how they fit together. And I'm around for a couple of days. You can ask me about the more advanced things. So one thing is, a lot of us don't write the algorithms to sample from things we call library routines. So a lot of us will call the functions in SciPy and trust and hope that they've been implemented well, and maybe they have and maybe they haven't been. But occasionally we need to understand how those generators work. And so if you do ever find yourself wanting to know how some of the standard non-uniform random number generators work, then there's a free online book that has some of the classic algorithms. It's old, so it doesn't have everything, but it has a couple of things I'll point out. One of the things you should know is how to sample from a discrete distribution. So I want to run a simulation that internally has 3 choices. It needs to pick whether to use option A, B, or C, and they have different probabilities. So the classic way of doing that is to lay out the probabilities on a stick of length 1. You pick a random number, you look along the stick some length. So I draw a random number u, 0.4, and I go, okay, I'm this distance along the stick. That's option B. And the probability of getting option B is a half, because half the time I'll land in that interval of length a half. So that's the obvious way to draw discrete random numbers, and I've written versions of this algorithm multiple times when I've been too lazy to work out how to call the library routine, because it's quite short to write the code yourself. But there are better ways, surprisingly, of drawing from discrete distributions, particularly if you want to draw many, many samples. So in the book I just showed you, there is a method called the alias method that's useful if you want to draw many, many discrete samples from an enormous distribution. So just last week, I found myself wanting to sample from a distribution with 2 million entries many, many times in a neural net training algorithm. And I pulled out this algorithm. It's very short. You can write this code so that every time you're drawing a sample, you're not searching along a stick with a million things on it. There's a constant time algorithm that can draw samples no matter how big your data is. So I'd recommend just knowing that these things exist and look them up when you need them. I think I've used this algorithm 2 or 3 times in my career. Question? Could I have used the max Gumbel trick to do that job? So the max Gumbel trick is a trick where for every option in your distribution, you draw a random number, you transform it in some way, and you pick the biggest number, and you pick that off. So if you had an enormous distribution, you need to draw, in my example, 2 million random numbers. So in this particular case, this alias trick, you draw a couple of random numbers, and it would be a lot faster. The max Gumbel trick I like. It's very short code, and if I have a small softmax, that's a trick that's worth looking up as well. There was another question? Okay. In the limit of an infinite number of options, we have a continuous distribution, and we don't want to explicitly lay out a stick with infinity things on it. So we end up doing integrals and inverting integrals if we want to sample from continuous distributions. And we can't necessarily do those integrals all the time. So here's the ideal thing we'd like to do in a geometric picture of it. There is maths, which I'm not going to go through. But the picture is if you've got some distribution that you want to draw a sample from. So here I've got a probability density up to a constant. What we want to do is draw points underneath that curve. So draw points fairly from the area under the curve, and then just read off where they are along the axis, and that gives us a sample. So here I've drawn 4 darts at the area under the curve. I've got 4 parameter settings that I read off, and those are fair samples. And if you work through the maths of how you would actually implement that, you need to compute integrals and invert them, and it corresponds to the continuous version of the stick thing. But you might not be able to work out how to do that. So in the core of a lot of code is this idea called rejection sampling, where you upper bound this curve. So I've got the distribution I want to sample from, and I've got some upper bound that's tractable and simple. And what I do is I sample points uniformly from underneath the tractable curve. So if the green curve was a Gaussian distribution, I know how to sample from a Gaussian. So I'd sample a bunch of points from the Gaussian. I'd pick random heights underneath the curve, and I would get these black points. A bunch of those are above the blue curve, and I throw them away. It's called rejection sampling because you reject things and just throw them away. And whenever you get a point underneath the blue curve, that point is a fair sample from the area underneath the blue curve. When we sampled from the green distribution, we didn't look at the blue one. We didn't fairly favor this area over this area on the left. And so this is an algorithm for drawing points from the area underneath the blue curve. And you might have used this algorithm more than you think. So if you've ever used MATLAB, when you type rand n in MATLAB to sample from a Gaussian random number, it's actually using rejection sampling. Amazingly, putting a tight stair-step upper bound over the Gaussian bell curve is the fastest way we know of sampling from a Gaussian distribution. There are many other ways of doing it, but MATLAB is several times faster than the SciPy algorithm, which uses a more classic method. And this is relevant to machine learning. So just, I think last year, there was a paper that looked at how these samplers work and said, we can convert these into a stochastic variational inference algorithm. So Christian Nasseth realized that if you have a library routine that does rejection sampling from a distribution, you can convert that into an algorithm to do stochastic variational inference with that algorithm. And unless you understand the guts of how these things are working, you wouldn't have that insight. Okay. Rejection sampling is mainly used when you really want samples from a particular distribution, but we're often interested in integrals. We don't necessarily care about the individual samples themselves. I like looking at the samples, but if we're reporting a number, it's not necessarily the intermediate step we need. So the other classic idea that you should all know about, and I know has been in a previous talk, is importance sampling. But it's so important, I'm going to tell it to you again anyway. So it's a trick for converting any integral into an expectation under one that we know how to sample from. So I have an expectation, and it's got some nasty distribution pi I don't know how to sample from. So what I do is multiply and divide by q. So as Shakir said in his tutorial, you multiply the integrand by 1. You haven't changed anything, as long as we didn't divide by 0. And now this is an average under q. we can replace averages under Q by sampling from Q and getting a discrete empirical average under the samples that we saw. And this original integral didn't even need to be an average, so that f pi together is really just any arbitrary function, f pi. So any definite integral that you want to solve that's got a bounded range, and you could transform it so it has a bounded range, you could imply importance sampling to. So this is something I routinely do if I've done an integral analytically. I will check it because I probably messed up, and I have had symbolic algebra packages confidently give me the wrong answer to definite integrals, so it's worth checking them too. It's a very tiny amount of code just to check you've got the right answer to something. Very useful to do. You won't see this trick used very much for prediction in large models using Bayesian statistics, though. And so why is that? Well, one reason is that we can't evaluate pi, so this isn't an algorithm we can actually run. If that is our posterior distribution over parameters, it has a constant in it that we can't evaluate, so we can't evaluate this ratio. So there's another version of importance sampling that you can use for Bayesian prediction problems. We sample our parameters from the distribution that we like, and then we compute this thing called an unnormalized importance weight, where we use the unnormalized version of the posterior distribution instead of the normalized version. And then we make these numbers add up to 1. So what this equation here has done is taken the sum of the numbers and divided by it. So maybe these numbers added up to 10, so I divide by 10, and now they add up to 1. I've normalized them. And what you can show is that if you've got an integral, a reasonable approximation to it is to replace it with a weighted average under this discrete distribution R. R is a distribution because it's a bunch of numbers that add up to 1. And implicitly what you're doing is an estimate of that underlying normalizing constant. So as an exercise, you can say, what would be a good Monte Carlo estimate of, well, an Monte Carlo estimate of this normalizing constant, and substitute it into the previous algorithm, and you end up with this version. So what would happen if we use this idea on the examples I've shown you? So here we've got linear regression. The blue is the underlying truth. We'll never know. We've got our data set. Here are 60 different samples from the prior distribution. That's a convenient distribution I've got kicking around, so I will use that as my proposal mechanism. I'll say, here are 60 samples from Q, and now I'm going to attach importance weights to each of these lines. And there's a nice interpretation here. What importance sampling does exactly corresponds to saying, I'm going to replace my prior with a prior that says one of these 60 lines is correct. No other functions are allowed. One of these 60 lines is the correct one. Which one is it? And then you do the inference on that problem. And the problem with that is that almost all of these lines are complete nonsense. Like, they don't go anywhere near the data, or they pass through only one or two of the data points. And so if you solve that inference problem and say, which of these lines was it, you know the answer. Here are, you say that purple line is the only one that went vaguely near all the data. It's not a very good fit, but it's the least bad fit, and all the rest are terrible. So just like in the underfitting example we looked at, if you make simplifying assumptions, one of these 60 lines is correct, you don't magically fix things by being Bayesian. You just ram all of your probability mass onto the least bad answer. So what this graph is actually showing is all 60 samples colored by how probable they are, and 59 of the lines have so little probability that their lines are indistinguishable from white on this graph. So I could go away and do something else, or I could go, I've got a fast computer, I'll just draw more samples. So here's the same figure with 10,000 samples drawn from the prior. So I said I'm going to have a prior that says there are 10,000 different possible functions. Which one was it? And I've colored each of those 10,000 lines in proportion to how probable they are. And the deep purple lines are the most probable, and the fainter ones are less probable. And now we see that we are getting an idea of how things extrapolate over here, what sort of things are plausible, and we've got tight beliefs near the data. So for this tiny, tiny model, importance sampling will work, and is a useful check of any fancier code you've written to check that they agree numerically. But it doesn't necessarily scale up to more interesting problems. So here is a nonlinear data set, and I have worked hard, or slightly hard, to construct a prior over nonlinear function. So it's a bit faint on this projector, but I sampled a bunch of gray curves that you can barely see, which are possibilities before I saw the data set. And just to show you I've got a sensible model, in purple I've got 12 samples from the exact posterior in this model. So I've got a model that can fit the data, is uncertain in the outsides, and it extrapolates. So it wasn't actually a Gaussian process, but it could have been. So if you've been to the Gaussian process tutorial, that's what it could be. And you could say, what if we didn't do all the Gaussian process maths? Could we do importance sampling to do the prediction here? So what I'm going to do is sample many, many nonlinear curves without looking at the data, which is a silly idea, and then use importance sampling to color the ones that turn out to be good. So here I drew 10,000 samples from the prior, and I colored them. And the least bad one is the one you can see, and the rest are so faint you can't see them. And it fits a lot of the data, but it's obviously wrong. It's sort of quite outside the error bars on a suspicious number of points. So 10,000 samples isn't enough. I've got a fast computer though, so here are 100,000. Oh, same problem. One of them is far better than 99,999 of them. Okay, here's 1 million samples. Oh, it's beginning to look better. But I've still only got one effective sample. It's saying one of those 1 million is far better than all of the rest. So I've got no idea of uncertainty. I've got no idea that I should extrapolate in different ways out here. And actually, the fit still isn't that great. And this is like a one-dimensional curve fitting problem, right? It's got a few parameters because I've got flexible curves. But most of us are interested in bigger data sets than this with more free parameters. And if you just randomly pick parameters, you're not going to get anything that fits your data. So we need more ideas if we want to sample from posterior distributions. But importance sampling isn't just a junk idea that we then forget about. It's inside lots of machine learning algorithms, and it's well worth knowing about. Okay, so those are the basic ideas, and what I'm going to do is move on to reviewing the basics of Markov Chain Monte Carlo that says how to explore the posterior distributions of models. Is there anything that you'd like to stop me with at this point? Okay. So, as was mentioned this morning, the idea of Markov Chain Monte Carlo goes way back to the paper was 1953. Presumably they did it earlier than that in the 40s. And I've just put this paper up because I wish one day I can write a paper where I can have such an awesome introductory sentence. The purpose of this paper is to describe a general method suitable for fast electronic computing machines of calculating the properties of any substance. It's perhaps slightly overselling the method, but it is a very general idea, and their fast electronic computing machines were not as fast as my one, so you can do a lot of stuff with this. The other reason I've put this up is because we refer a lot to the Metropolis algorithm. He's the first author of the paper, right? These author names are in alphabetical order. Mathematicians often do that, and according to Marshall Rosenblatt, who I've got a link here, wrote a summary of this paper, the contributions to this work, as usual, were not even. They provided different things. So Nicholas Metropolis had an important job back then. Fast computing machines were new and an amazing thing. So he was someone who was in charge of running the computer, but apparently didn't have anything to do with coming up with the algorithm, writing any code, running any experiments, didn't write any of the paper, really didn't have very much to do with this thing. So Marshall Rosenblatt claimed that he was the one who came up with the algorithm, but it's hard to verify that as all the other authors are dead, so I don't want to claim that that's definitely true. He also said that his wife, Ariana Rosenblatt, wrote all the code, ran all the experiments, which I think is sort of interesting to know. Okay, so the idea of this paper, which Edward Teller, father of the H-bomb, apparently had, was to say we've got a complicated system. For them, it was things to do with nuclear physics. For us, it's statistical models. And rather than simulate the model lots of times or simulate the physics, which is complicated, involves differential equations, what we're going to do is pick something else that we can simulate conveniently on a computer and use that to give us insight into our model. And what Marshall Rosenbluth came up with was, we're going to simulate a Markov chain. So Markov chains are these things that say we've got a sequence of variables. So here I've got a sequence of a whole bunch of different settings of the parameters. And the probability of the next element in the sequence that you visit, given the history, only depends on where you are now, or the previous step. So the transition probability from the current parameters to the next parameters is all you need to know to define a Markov chain. And Markov chains can do several things. They've got several behaviors, and there were figures just like this in the previous talk, but it's important, so I'll say it again. One thing you can do is just diffuse around. So here's a Markov chain that started here, and it took random steps. So if every step is just a Gaussian distribution centered at where you are now, with some variance, then this is what the Markov chain will look like, and it moves quite slowly. After s steps, you've moved a distance of square root of s. So, and if you wait a long time, it will just drift off to infinity. It's a boring sort of diffuse process that doesn't tell us anything. Another thing a Markov chain can do is collapse to an absorbing state. Have something that just falls into a black hole and never returns. Probably not useful if we're wanting to get an idea of the space of our model. And another thing a Markov chain can do is enter a cycle so that it visits some subset of the space and zooms around it. And maybe if you know how many steps it's run for, you can predict where it will end up or which island it's going to end up in. So these chains that blow off to infinity or have particular pathologies are not the ones we're interested in. And if a Markov chain doesn't do any of those things, there's only really one other thing it can do, which is to have an equilibrium distribution. So what we're interested in are Markov chains that we start somewhere, and they might look as if they fall into a black hole to start with, but they don't collapse to a point. They continue to move around some part of the space, preferring some regions of the space to others. And if you look at the places the Markov chain visits, so the blue points are just a bunch of points that the Markov chain visited without drawing the green line everywhere, those points asymptotically come from some equilibrium or stationary distribution. So when I was in high school, the maths exercise would be, here is a definition of a Markov chain, derive the stationary distribution, and you would do a load of algebra to work out what the properties of the Markov chain are. What we want in statistics, or they wanted in physics, is to go the other way around. We have an idea of what equilibrium distribution we want. We want to explore different settings of our model that explain our data, and we construct a process that will do that for us. It will explore those different settings of the model. So what we want is that if we run this Markov chain for a really long time, so in the limit of taking infinity steps, the distribution over the model setting we end up at is a sample from our target distribution. So in our linear regression example, we would get a slope and intercept, which is a plausible fit to our data. Not the correct one, not the best fit, but just a plausible fit. And then we can run it a bit longer and look at other plausible fits. So there's a load of technical terminology around Markov chains. The word you'll see thrown around a lot is ergodic. People will prove their Markov chain is ergodic. And when you see that word in a paper, I'm afraid I can't tell you what it means, because it means different things in different papers. But the main thing of what it means is that it doesn't matter how you initialize your Markov chain, it's still going to work. So no matter what settings of the parameters I pick for my model to start with, when I initialize my Markov chain, might be a slope and intercept that doesn't go through the data at all, I will fall into some region of parameter space exploring slopes and intercepts that match my data. And as long as you show that your Markov chain can get everywhere in your space, the moves that you're picking aren't trapped in some island, then it's usually pretty easy to show in theory the chain is ergodic, although in practice you don't know if it will really explore all of the settings of your model, and you might want to use more advanced schemes like nested sampling or annealing methods. Okay, so how do we do this thing? What we need to do is know what are we going to prove about a method so that we get this property. And the one thing that you need to prove that you have to prove, there are other things you might want to prove, but the one thing you have to prove about a method is it satisfies a basic self-consistency condition, and that's this equation on the bottom. And this self-consistency condition says if you run your chain for a long time, so that you've got a sample from your distribution, then if you run it for one more step, you want where it goes after one more step to also give you a plausible sample from your distribution, or a sensible model fit to your data. So if some oracle said, here is a plausible line, here's a slope and intercept that goes near your data, you want to design a Markov chain so that if you nudge that slope and intercept and just look at where you end up, that's also plausible. So in maths, averaging over a starting point and looking at where you end up, that gives you the distribution over where you are one step further on. That distribution should be equal to your stationary distribution. And that's the one thing that we need to prove about these methods. And it seems a bit daunting because we've got to prove something about our whole space and it involves an integral. But it turns out not to be that hard to prove. I've got an appendix slide where I could show you how to do it at the end of this time. I think of this a bit like yogurt making. When I was a kid, my mother said, oh, we're going to make yogurt. And I was like, awesome. And she said, OK, the first thing we need is some yogurt. And I was like, what? We were going to make yogurt? Like, this isn't cool. Like, the first thing we have to do is go to the store and buy some yogurt. Like, that defeats the whole point of making our own yogurt. So sampling looks a bit like that. It's like, to get a sample from the distribution, the first thing you need is a sample from the distribution. You need to already have solved the problem. It seems like cheating and circular. But if you satisfy this condition, and you show that your chain can get everywhere, that it's ergodic, it turns out that pretty generally it means that no matter where you start, if you didn't buy the yogurt, you didn't start with a sensible setting of the model, the equilibrium distribution falls in, and all you need to do is run your Markov chain for a long time, even though you only proved something about what happens on one step. So the classic algorithm that even if you don't run, you should sort of know what the basic version is the Metropolis Hastings method, this slight generalization from this paper from 1953. And it works as follows. We start not with a good explanation of our data, with an arbitrary setting of our parameters. And the proposal mechanism we use is an arbitrary distribution. So this distribution Q could be a Gaussian perturbation. So by itself, that would define one of these diffusive Markov chains that just wander around and by itself would wander off to infinity. But then what we do is we don't accept all of those steps. So at the beginning of the algorithm, I proposed going out here, following this red line, and the algorithm goes, nope, that makes things worse, don't go there. That made things worse too, don't go there. And then I proposed a setting where things got better, and the algorithm accepted that move. It accepted a whole bunch more moves as I got towards the plausible region of parameters. And then every so often when it tried stepping out to sort of bad settings of the parameters, the algorithm contains you in this region and says, no, don't step out there, you're not matching the data very well, stay within this region. So what I've described so far sounds a bit like an optimizer where you wiggle and you only improve things that accept. So the algorithm does always accept things if you fit the data better, but it doesn't always reject things if they get worse. It just sometimes rejects them. And it chooses the probability of accepting the move carefully so that you end up bumbling around the whole space of plausible parameters and not wandering off to infinity and not collapsing into a point. And this equation gives that acceptance probability, and it contains a ratio of how good the proposed parameters are compared to how good the old parameters are. And it only involves these unnormalized probabilities that we know how to evaluate. So for our model, this is the probability of everything. We say at this point in the Markov chain, we've got an explanation of our whole model. Theta here in everything we don't know, choices of outliers, parameters, noise levels. We say if we assume that this is what happened, how probable is it that that bunch of stuff would happen compared to this alternative we're currently considering? And that's something that we can evaluate. And then very simple code. So I'll show you some code in a minute, but it's very short to run this algorithm. And the generalization by Hastings, who's a statistician in Toronto in the 1970s, was to introduce this correction term that allows you to get creative about what this proposal mechanism is. So if you just bumble around using Gaussian noise, you don't need to worry about this term. But if you've done something clever and come up with a proposal that isn't symmetric so that this ratio doesn't cancel, then you take into account that proposal mechanism. So if you always propose going to some particular place in the parameter space, you would end up with a Markov chain that would just like go to that one good setting. Whereas this ratio says, oh, hang on a minute, it looks like it would be hard for you to come back out of that hole that you keep proposing to go into. Maybe we shouldn't accept that move. So including that term makes this simple algorithm actually exceedingly general, because you can go away and make this probability an approximation to your model, or use insights about how to navigate the space of your parameters. You can do all sorts of things and put them in there. Out of interest, who's implemented this algorithm or run some version of it? Yeah, okay, so like a third of you. Okay, so you're all experts, so I'll ask you a question. No, a third of you are experts. I'll forgive the other two-thirds of you. So let's imagine that I've just got one parameter, and it ranges between 0 and 10. And I've decided to run this Metropolis algorithm, so I'm going to run a Markov chain that one. So I look in my problem, and I'm going to get clever about the proposal. So I look in my problem, and I decide that there are two special regions that are worth thinking about. The region between 0 and 1 has some meaning in my model, and the region between 1 and 10 has some other region or corresponds to some other behavior. And I want to make sure I see both of those regions. So I decide to make one of the proposal that I do sometimes to be this thing defined by maths that you won't want to pass, so I'll describe in English what it does. If you're between 0 and 1, it says what fraction of the way between 0 and 1 are you? So maybe 90% of the way through. Teleport to be 90% of the way through the other region. So if you're here, propose going to here. And the other way around. If you're 90% of the way through the second region, teleport to be 90% of the way through the first region. Or if I was at the left-hand edge of the second region, teleport to be at the left-hand edge of the first region. So it's just a move that allows me to bounce between these two regions and make sure that I see both of them. And to be ergodic, I need to do other things. So I could do this half the time, and maybe the other half of the time I drift around within the region. Okay, so I've now got a proposal mechanism. And if I were naive, I'd say, well, here is the Metropolis Hastings acceptance probability. My proposals are deterministic, so the probability of proposing going here at the right-hand edge of this region from here is 1, because I always do it, and the probability of going back is 1, because I always do it. So that's going to cancel, and I will just use the ratio of the probabilities here. And I've just told you a massive fib, it's wrong. We can see this algorithm won't work. So for example, consider the uniform distribution between 0 and 10. If I drew a sample from the correct distribution, I've got my yogurt making machine and I draw uniform random numbers, then 10% of the time I will be between 0 and 1, and 90% of the time I'll be between 1 and 20. And I can say, what would this transition operator do after one step? So after one step, all of the points on the right would go to the left, so 90% of the time I'll end up in the left, and 10% of the time I'll end up on the right. So I started with a uniform distribution, and after one step I've upset it, I've schlunked all of my mass into a spike on the left. So this is an invalid algorithm, and if you're going to like read the algorithm in the textbook and want to run it and get creative, then you need to understand what I've just done wrong, because otherwise you might do the same thing wrong. So who immediately knows what I've done wrong? Okay, talk to your neighbor for 3 minutes and see if you can figure it out. Okay, so does anyone have an answer for me? Any answers? Okay, so for some of you, I've gone quick on the algorithm, but for other people, if you run MCMC method, it's sort of worth knowing what to look out for. And one of the things that you need to be a bit careful of in all of these probabilistic algorithms is the difference between discrete probabilities and probability densities. So a lot of the Markov chain maths is trivial in the math sense of trivial, you know, after you've looked at it for 5 hours, you figure it out. It's easy for discrete spaces, and then we go, oh, well, our continuous spaces are a bit like that, so we'll just replace our probabilities with probability densities and hope it works out. These things here, these proposal probabilities, are really probability densities if we've got a continuous range between 0 and 10. And so those numbers aren't 1. If you propose going to some point in a continuous space, that's a spiky distribution that's infinitely narrow, and so it has to be infinitely high. It's a Dirac delta function. So these numbers are actually infinity, the probability density of going from one place to another. And you should be pretty suspicious if I say in my maths, well, I've got infinity divided by infinity, so that's 1. Because you know that's the way where sort of dodgy things happen, and you need to be a bit careful. And in general, if you're ever doing anything with deterministic transformations or deterministic constraints, where you say this real value has to be exactly here, or I'm going to transform this real value from this place to precisely this other place, then it's just a flag that it's worth checking whether you need to be careful of anything in particular, whether that's the one place that I've embarrassingly in my career messed up, and there's a mistake in my PhD thesis because I've not been careful about this issue on one page. And so there are various ways of being careful. The low-tech way of doing it is to discretize and see if you can think about discrete probabilities. So in this problem, if I discretize my axis very finely, then on the right-hand side, there would be 9 little boxes that would all actually collapse to the same box on the left-hand side. And so the probability of going from one of those boxes to this box would be 1. But what's the probability of going back from that box to one of these? We've maybe forgotten where we've come from if we discretize. So either we go to one of these boxes, so a bunch of the return probabilities are 0, or we maybe pick one of the boxes at random, and so the probabilities are all a 9th. So it's harder to go from left to right than it is from right to left. So the ratio of these proposal probabilities shouldn't be 1. It should be 9 or a 9th, depending on which direction you're going in. And that penalty term would stop you from slumping all of your probability mass over to the left. If you want the more formal maths version of that, Peter Green's paper in '95 on reversible jump Monte Carlo claims to be a paper about transdimensional spaces and a load of stuff, but it's really about how to deal with deterministic transformations, and it tells you how to formally derive what that ratio should be as a Jacobian of the transformation. And so most of you won't have followed that right now, but you squirrel it away in the back of your head as, if I'm ever going to do anything deterministic within my Markov chain or within any probability maths, look up what you're doing, or maybe run a test case and check that it's doing what you think it's doing. Okay. So, what I think I'll do is show you an example of what this stuff looks like, because for those who haven't run these algorithms, it's maybe a bit abstract. So I'm going to show you an inference problem that wasn't at all difficult, but it's just a nice graphical problem where I can show you sort of what it means to move around settings of a bigger model. So this is a Kaggle competition from a bunch of years ago, and the top 2 entries ran MCMC on the problem and then did some other stuff to make sure they won the competition. I came second, but the person who came first did much the same thing as me, and there's a write-up. We both had write-ups of how this works, and there's code on my website, so you can follow along if you want. And in this problem, they had some simulated data, so they knew what the ground truth was, and they could see what was going on. And here's a cartoon of like an easy version of the problem. These are synthetic galaxies in the sky. So most galaxies are slightly elliptical and they have an orientation, and the orientation is being visualized by the line on this diagram. And if there's dark matter between you and the galaxy, it warps the light and it changes the apparent orientation of the galaxy. So if there was dark matter at this location, you would end up tending to see galaxies that are arranged apparently in a halo around that dark matter location. It's an illusion, it's the light being bent by this gravitational lensing, but this dark matter that we can't see, you can detect that it's probably there from this suspicious ring pattern in the data. But you might fantasize that there's dark matter in other places where there isn't. Now, in this extreme example where the effect is large and there's this obvious halo, we can see where the halo location is, and if we initialize a Markov chain somewhere and run it, then we'll end up bumbling around very tight in a very tight ball in the middle of this location, saying this is where we think the dark matter is. So what would our Markov chain be doing? I initialized it with a couple of numbers saying where in the sky am I going to guess the dark matter is. But actually this Markov chain was probably in a 5-dimensional space because the dark matter halo has mass and it has a shape and profile of how that mass is distributed. So I'm going to have a few parameters that describe what the dark matter is like, which I can't see, as well as where it is. So I run a Markov chain in a 5-dimensional space over everything I don't know about the dark matter halo. And what the Markov chain does is move that 5 numbers to another 5 numbers and say, well, how plausible is this setting of the model? How well does it explain this halo effect? And you bumble around this 5-dimensional space that I'm showing you into, each time evaluating how plausible does everything look. If I assume this is what's going on, does that look like a good idea? I'm using a method called slice sampling here that does some fancy adaptation so that it's actually converged very quickly. But you don't need to know the details of what's running. The important thing is to know it's a Markov chain that's doing this exploration. Now, for this example here, no real point doing MCMC. You could optimize and find this point. You could do all sorts of things to estimate how uncertain you should be around that point. MCMC is just one thing you can do, and it's a very small amount of code. But a lot of skies look more like this. So you go, where is the dark matter? In this challenge, they gave us some information that we wouldn't really have. So they said, in this patch of sky, there are 3 concentrations of dark matter. So normally you'd have to do inference over that number as well. But we were told there are 3 locations. Where are they? And we weren't told how massive they were or what shapes they have and things like that. So who thinks they can see where the dark matter locations are? Yeah, it's difficult. After you stare at hundreds of these, you can actually spot some locations, but you're not necessarily correct. So what we do is we throw down just some setting of our model as a starting point. So that, by the way, is the answer. So that dark matter halo is very, very light and doesn't have much effect. But these ones, when you look, you can actually see a very slight lensing effect around them. So in our algorithm, we've got here, I've just thrown down a dark matter location there, one there, and one somewhere else in green that I've lost. And I run one step of the algorithm, there it was, and I go to another new location. So I'm just comparing 2 locations. I started with a guess. I try moving somewhere else and go, is this better? Does it match data more? I then move to another guess. So you're seeing a Markov chain that looks like it's running in a 6-dimensional space. It's moving these 3 locations around. It's actually running in more like a 15 or 20-dimensional space because it's moving around a load of other numbers, the masses of the dark matter halos and things like that. So you run that for a long time and it explores a bunch of places. You run it for a lot longer. And what I've done here is plotted a load of locations of where these different bits went. I can throw away the colors, which are a bit arbitrary. It was just saying which chain I was calling the first dark matter halo, which the second. And I could color them with the masses that it imagined they had. So the inference I've got here is I'm pretty sure that there is some dark matter concentrations in around these locations. I don't know exactly where, I don't know exactly how massive, but there does seem to be something there. There could be a dark matter halo location here, which there was, but there could be one in all sorts of other places. So if there is one there, it's not very massive, and I can't be sure. There are all sorts of places where there could be dark matter halo concentrations. Now, this sort of problem is hard to summarize with the variational inference that you saw earlier in the summer school, because there's no short, neat description that says, oh, I can put down a Gaussian elliptical ball saying what to believe here. It's a mess. And there's a lot of things that we don't know as well as things we do know. So we've got some idea of where there could be dark matter and what it might be like, but we also have to admit that we're not very sure, and it's quite complicated to describe exactly what we believe and what regions we think there might be dark matter halo. And if we don't want to conclude spurious physics about how dark matter halos interact with each other, then we've got to be very careful about communicating that knowledge to the downstream physics analysis. And that's what this Kaggle challenge was about. Not just guessing locations. They don't care about just people who are good at guessing. They wanted you to understand the uncertainty so that you didn't spuriously conclude that dark matter attracts more than real matter just because some fitting procedure has a shrinkage effect and tends to put things close together. So this was a case where having a set of explanations is a very easy way of then doing the downstream analysis. And so it's sort of a nice fit. But not all statistical problems you will do should be done with MCMC. A lot of statistical problems I work on aren't done with MCMC, but sometimes it's exactly the right thing. Okay. So there are a whole bunch of methods, and I've given much longer versions of this tutorial where I've explained how some of the others work, and some of those are online. But for the moment, I think what I want to get across is this idea of what the Markov chain does for you, and then you know there are different methods that do the same thing, but some do it better than others on different sorts of problems. So Hamiltonian or hybrid Monte Carlo was used for neural networks in the 90s. That was Radford Neal's PhD thesis. And that code still works. So he wrote that code in 1994, but it doesn't have any dependencies, and it's written in C. So it turns out it still compiles, and it still works. I've used it for real problems, and it's a good idea. You're not going to be able to solve, say, ImageNet recognition using that sort of neural network and that sort of Markov chain. It doesn't scale to that size of model. But a lot of problems only have 1,000 variables, or you can reduce them to 1,000 variables using some pre-trained neural net. And this sort of thing could work. If someone could run these neural nets in the 90s, you can sure run them now when you've got much faster computers. The Kaggle competition I showed you used a method called slice sampling. Radford Neal's 2003 paper and the discussion is very good and readable, but also David Mackay's textbook takes you through it. And there's a special version for Gaussian processes called elliptical slice sampling, if you're following on from Neil Lawrence's tutorial. And there's some messages here for those of you who are developing the methods as well. So in astronomy, MCMC methods are still very popular, and it's interesting to see what they use and why. So for example, a lot of papers in astronomy use this Python package called MC. So there's a joke in there. And why do they use that package? The main reason they use it is that you can pip install it, and it's incredibly easy to use. So you give them a function handle for the probability of everything after pip installing. It sets up a whole ensemble of different settings of the model, and explores your model parameters, and it automatically multi-threads. So if you've got a laptop with 8 cores, it will use all 8 cores. And for a bunch of problems in astronomy, it's enough, and it works. It's not really everything we know about MCMC methods. It will fail horribly on some problems, and you do need to know how to use it. Like if you don't optimize your model before, it's not actually very good at this burn-in phase, falling in from the initial setting. But it's a message that easy software wins. So I have told people to use MC when I looked at their problem and I went, yeah, that will work, over my own methods that I've published, where my methods, I thought, oh, this thing I did in this paper will actually be slightly faster on your problem. But I don't have a pip installable package for it that will be as easy to use as this. And so I think this is good enough. So it's not good enough to just write the paper. You've also got to really look at how people use it and how they install what they're currently using and copy that if you want to have the impact. And I'm kind of just telling myself off in front of you so that maybe next time I give one of these tutorials, I can have my own package there. Okay, so there are a bunch of practical issues, and I'm sure that if I offer questions, a lot of you will immediately say, oh, well, how do we know that this stuff will work? So I'll preempt a couple of those as quickly as I can before wrapping up. So one thing is that when you're exploring your model space, you might worry it might take a long time to get from your initial condition to sensible models that match your data. So there's a whole literature on how to look at your Markov chain and things that will at least tell you when things have gone wrong. They can't guarantee that you've run your chain for long enough, but they can often tell you when you haven't, and you usually haven't. So those are useful methods, so there's some references there. But what I'd like to do is tell you, no, that isn't the first thing you should think about. Don't think about the maths. Don't think about whether it's valid and what the asymptotic convergence is and stuff. The first thing I think about is that I suck as a programmer, and my code is probably wrong. And I'm not the only person. All of you will be brilliant, but I'm not the only bad programmer in the world. John Guecki, who is a statistician, is another one. He wrote this paper called Getting It Right. We'll want to get things right. And this paper is about a check you can run on your code to check that whether your code has bugs in it, specifically your MCMC code. And he didn't want to embarrass anyone else and, take some paper and show that some other people had been wrong. So he got one of his own papers from 20 years previously, untarred the code and pulled out the crufty Fortran code and showed that his own code was actually wrong, and his published results resulted on MCMC code that was wrong. And I'm very grateful to John, because this check is very useful, and I have been on the verge of submitting something late, in the last hour before a paper deadline, and I've gone, I'm just going to rearrange this linear algebra to make it slightly more numerically stable or slightly faster. And then I've rerun the check that John has advised and gone, whoops, and I'll revert that change before committing my code. So this check has saved me from embarrassing myself, and it would save people from getting wrong results and publishing results that are wrong. And this sort of research is what I think we need to do more of in machine learning in general. A lot of the things we do are very hard to check, and we need to be looking out wherever we can for ways to be able to write unit tests or integration tests for our code. And this is just one of the ideas for MCMC. Okay, so I should wrap up. Summary of what I've said is, for probabilistic inference problems, you write down the probability of everything, and then there's a bunch of methods where you give them a function handle to that method, and it will explore your model for you, and you can then look at it and you can make predictions. There are a bunch of different methods, and I'm not going to be able to give you a flowchart of how to pick from them, but rejection sampling, exact sampling, that's what you'd use inside a simulator. I want to sample from particular probability distributions, I have to do it right. Those are the methods you'd use. Importance sampling is a really useful trick in lots of other contexts, in reinforcement learning, inside stochastic optimizers. Probably not the best thing for inference unless you're checking your code. So for these larger parametric inference problems, MCMC is a good starting point. There are other approaches. But these black box methods like size sampling or the Metropolis Hastings I showed you, if you're prepared to tune it, is something you could do. And these Monte Carlo methods are also these Monte Carlo methods are embedded within other algorithms. So there are stochastic optimizers that run MCMC within them, and there are other meta methods like annealed importance sampling, sequential Monte Carlo, John Skilling's nested sampling, where you need to have an understanding of what Markov chains do so that you know how they work within this larger system. You'll have the slides, so there are some references to some tutorial materials. And if you want to play with code for this machine learning summer school in Cambridge, I wrote a demo. I'm afraid it's in MATLAB, but if one of you emailed me, you could probably guilt me into porting it into Python. There's a bunch of examples with Stan, which is a package that contains a good Hamiltonian Monte Carlo implementation, and there's code for this demo I showed you if you wanted to work through that. So with that, I'll take any questions.